Hello everyone. Due to the request of some people, I'm going to do a quick video over some of the practice problems and work them out as a way to help out. So I'm going to start with number 16 on the packet here, which is our HIV question. I'm going to do a couple of them and then I will upload this for you all to see. So let's get started. So number 16 states, suppose a researcher is interested in a new treatment plan for increasing CD4 cell count in an immune-compromised patient with HIV. In order to investigate the new drug, the researcher gathers a group of 48 individuals with a mean CD4 count of 317 cells per millimeter. After treatment with a standard deviation of 24.6, test a hypothesis that a mean CD4 count has increased above the goal of 275 cells per milliliter. Write out your hypothesis and correctly interpret your p-value. So first thing, after reading a question, always figure out what you have. So what we have here is a group of researchers who are looking at HIV immunocompromised individuals and a new drug. So they gathered a group of 48 individuals with a mean CD4 count of 317. So since this is our sample, right, they took a group of 48 people, so N is going to equal your 48, and their mean CD4 count was 317. We know that's our X bar, right? That's not from a population, it's from a sample, so it's our X bar equals 317, right? And we have a standard deviation of 24.6. All right, so then what else do we know here? And then we know that we want to test a hypothesis that the mean CD4 count has increased above the goal of 275. So we know our goal is 275, and we want to test a hypothesis of that. So we know that's going to be our mu is going to equal 275. All right, so this is what we know. Let's correctly write it out. Oh, and we know our alpha level is 0.01. So our null hypothesis is going to state that mu is equal to 275, right? That is what we're testing against to see if the drug increased the goal of 275. Alternative hypothesis is going to state that mu is going to be greater than 275, right? We want our T cell count to be above 275. Now we throw in our, find our Z value here. I'll write it out. So Z is going to equal our X bar minus mu naught over the standard error of X. For time purposes, that's going to be 317 minus 275 over 3.5507, and that's going to give you a value of 11.8286. Now, that's your Z. Now remember, if you go to the back of the book, we're not going to find anything above 3.49, and therefore we're going to say, because a value at 3.49 is going to be 0.9998, and then since this is higher, it's going to be greater than that, right? So we know our p-value is going to be at least 0.001. So anything above 3.44, say p-value is 0.001. In actuality, this will be much smaller p-value, but we don't know the exact value of it without statistical software, so we'd state our p-value. P-value is going to equal 0.001. We look at our alpha level here, alpha level of 0.01. Since our p-value is less than alpha, we're going to reject the null hypothesis. And then that's how we interpret our hypothesis. We're going to reject it because our p-value is less than alpha, and this is proof that the drug that they are investigating is in fact increasing the CD4 count of this individual. All right, so moving on to number 17. How many participants are needed to be enrolled in a study looking at early onset of dementia in a population of middle-aged adults with a power of 90%, assuming the population has a standard deviation of 7 years, and the detectable difference of interest in age is 6 years. Perform a sample size calculation at 95% confidence. So first thing we know, we're trying to perform a sample size calculation. Our formula for sample size is N. It's going to equal our variance, or standard deviation squared, times the Z of 1 minus beta plus Z of 1 minus alpha over 2 squared over the detectable difference squared. I think the hardest part of this equation is understanding your z underscores here, which are your z percentiles. So let's start from the beginning. Our standard deviation we said is 7, so it's going to be 7 squared times by 1 minus the z of 1 minus beta. So we all know 1 minus beta equals power. If we know our power is 90%, shown here, so 1 minus beta equals 0.90, right, 90%, then 1 minus beta equals 0.90. So z of 1 minus beta is just the z of 0.90, which if you go to the back of the book and look up your z of 0.9, you're going to get a value of 1.28. It's not negative, let's get rid of that. And then plus your z of 1 minus alpha over 2, so if you take your z of 1 minus alpha over 2, well, alpha is not stated, but alpha has a relationship with confidence. 95% confidence is an alpha of 0.05. Confidence in alpha are always going to give you 1 or 100%, so our alpha level is 0.05. So if we put z of 1 minus 0.05 over 2, you get 1 minus 0.025, which is 0.975. So z of 975, you look up in the back of the book, gives you a value of 1.96. Value squared all over the difference worth detecting. So the detectable difference in age of interest is 6 years, so 6 squared. Once you work all this out, you'll get an answer of 14.3. Now, you can't get 0.3 of a person, so we round this up to 15, and even if you wanted to be more accurate, you'd probably even round this up even higher, because they'll be lost to follow-up, people who just decide not to pertain to your study, people might die in your study, might move, relocate, who knows the answers for that. So you always want to have more, because this is the minimum number of people at this particular power and confidence you need for this type of test. Moving on to question 18 here, a research team wants to investigate the impact of increased sun exposure to a decrease in depression. In order to do so, the team gathers a simple random sample of 124 individuals with a sample average score on the Generic Depression Scale, or GDS, of 7.5 from a population with a standard deviation of 0.4 after consistent sun exposure over 7 hours a day. Assumed clinical diagnosis for depression can only be given with a GDS score of 9. So this research team is investigating that if people who stay in the sun have consistent sun exposure above 7 hours a day are going to score less on the GDS scale compared to people who don't. So what they did is they found people who stayed in the sun above 7 hours a day. Your N here is 124 individuals who did stay in the sun 24 hours a day. When they took their GDS scale, they had an average of 7.5, and they had the standard deviation of 0.4. So when we write out our hypothesis, our H naught, our null hypothesis, is mu is going to equal 9, right? This is based off of a GDS score of 9. They're trying to see if people stay in the sun longer than 7 hours a day are going to not be clinically diagnosed for depression. A score of depression is a score of 9 on the test, so they're trying to score less than 9. So that's your null. Your alternative is going to be mu is going to be less than 9. And now we go and calculate our z-score. Our z-score here is going to be 7.5 minus 9 divided by the standard error of x, which I already did, was 0.359, which is going to give you a value of negative 41.7827. As you can see, this is an area that's very far to the left of the mean. Remember, this would be your z-score, so this is like negative 41 standard deviations. So it's super, super small, which is going to give you a p-value of a real p-value would be point like 0.00000001, but for all intents and purposes for the class, we were just going to state that it's going to be 0.001. So p value is going to equal 0.001, and we're going to reject the null hypothesis. So is the team correct in their results? Yes. If you are exposed in the sun over 7 hours a day, this constant sun exposure will shows that you'll score less on the GDS scale, or the generic depression scale, and therefore not be clinically diagnosed for depression as long as you're in the sun for 7 hours a day. And we also know this to be true: the more sun exposure you have, the less likely you are to be depressed. Okay, I will do this last problem. I'm not going to read the whole problem out, just because we're going to run out of time here in the video. And this one is, I think, a really good one because it shows how you can use this to your advantage. So the question is basically asking girls who get vaccinated for the HPV shot between the ages, they normally get vaccinated between the ages of 11 and 13. Are they more willing to engage in intercourse at an earlier age versus girls who don't get the shot? So the researchers are trying to claim here for this particular problem that if you do get the shot, you're more likely to engage in sexual intercourse at an earlier age. The information they give us is your N is going to equal, they had 56 girls that did get the shot. They had their average age of intercourse was 14.6 years. The population age was mu equals 16.7. So girls, on average, for their age for first intercourse was 16.7 years, with standard deviation of 1.2 years. So our null hypothesis that they're stating is the mu is 16.7. The alternative hypothesis for them is that mu is going to be less than 16.7, right? They're trying to prove that females who get this vaccination have intercourse at an earlier age. So we throw in our Z testing statistic, which is going to be 14.6 minus 16.7 over the standard error of x, which is 0.1604. It's going to give you a value of negative 13.0922. We know, once again, that this value is about 13 standard deviations to the left, and so it's going to give you a very small p-value number. We can't actually calculate it with the chart given to us, so we're going to say the p-value is 0.001. At the very beginning, it said alpha level is 0.05, so our alpha level, our p-value is less than alpha, so we are going to reject the null hypothesis. And this study is proving that girls who are vaccinated earlier are having intercourse at an earlier age. That is what this problem is telling us and suggesting. Okay, so I'm going to stop the video there. That was the kind of harder ones in the packet. I just wanted to go over and write them out. And if you have any questions, always feel free to get in touch with me via email or come to my office hours, whatever works best for you. Until